of y equals 2x squared over x squared plus 4. And I would put this firmly in the place of you got to show some work. I know it doesn't say that. If I wanted you to on a quiz or test, I'd say it. I'm just going to say it out loud this time. Please do show some process as to how you arrived at your conclusion. I think we're going to do a little bit more with this than I originally thought. This hopefully will be good. So if you're going to check where all the horizontal asymptotes are defined by the extreme right end or the extreme left end of the graph, right? When we say extreme ends, we're talking about the limit as x approaches what? Infinity or negative infinity, right? Sometimes you can have different behavior on the right and left. Sometimes it's the same behavior, right? So maybe I set something like this up. Limit as x approaches maybe positive infinity of 2x squared over x squared plus 4. And then maybe I try the same sort of thing, limit as x approaches negative infinity of 2x squared over x squared plus 4. So you want to check both ends, both left end and right end, in order to be certain that you've collected all horizontal asymptotes potentially. It could just be one or it could be two. So how is it that we then evaluate these? I want to give you a couple of options here. So if you're supposed to show your work, you can't just be like, hey, I used a pre-calc trick with the whole degree ratio thing and blah, blah, blah. So the answer is y equals 2, right? If you're supposed to show your work. That's not very rigorous. So you could do this. You could say division by the degree of denominator. And so that would be limit as x approaches infinity of 2x squared over x squared over x squared over x squared plus 4 over x squared, which would then give us limit as x approaches infinity of 2 over 1 plus 4 over x squared. And as x approaches infinity, that 4 over x squared approaches 0. And so you end up with 2 over 1 plus 0, which is 2. So then you could say, well, my horizontal asymptote is at y equals 2. Make sense? And if you did a similar idea with that limit as x approaches negative infinity, you'd get very similar results. So in this case, there is only one horizontal asymptote. This is kind of where I was going to go with this, but a couple of folks asked me about L'Hopital's rule. So I thought, last year at the reading, there was a L'Hopital's rule question on the AB exam, and it was like the most missed. It was horrible. Like, it was so terrible. I didn't grade any of your papers, so I can't say. Hopefully you guys all did. Hopefully you guys defied the trend and did awesome on that one. But as a general trend, it was pretty terrible. So let me show you what you do here. If you wanted to use L'Hopital's rule, and I know Jaden and Jeff haven't heard of this yet, so I'm not going to be holding you responsible for this at this point. Just use the technique unless you want to figure this out. This is navigating L'Hopital's rule is kind of devious because it seems like a really easy process, but showing why you're allowed to use it is actually a pretty narrow path. There's really only one really truly rigorous way to do this. So I'm going to show you that way. So maybe in your head, maybe you look at this and you're like, all right, x is getting huge. So, oh, look at that. So that means the numerator would be getting really, really huge, right? 2 times something huge squared. It's going to be approaching infinity, right? And the denominator, same sort of thing, like something huge squared plus 4, something huge. So here's what you do. Here's how you actually should be writing this down. We'd say something along the lines of limit as x goes towards infinity of the numerator equals infinity, and limit as x approaches infinity of the denominator. They both independently equal infinity. And if you wanted to put little arrows there instead of equals, there's nothing wrong with that. But we're basically saying the numerator is increasing without bound, the denominator is increasing without bound, and that's one of the conditions for L'Hopital's rule. What's the other condition? Say again? Zeros instead of infinities. That's right. So if you had a 0 for the numerator, 0 for the denominator, that's another condition. So then what you can then do is say, well, L'Hopital's rule's condition has been met, So what I can do is I can differentiate the top. We'll look at a proof of this later, but you can differentiate the top, and you can differentiate the denominator like so. And then we can retry the limit. But did you notice the x's would cancel out before we did anything with the limit? So you really could just say, well, hey, this x would cancel with that x. And once that happens, there's nothing for the limit to apply to. And so this just ends up equaling 2. The thing that most folks missed when they missed this was this, the condition. Did you actually show that the condition was met? So L'Hopital's rule is this theorem that's provable and it works and everything. But as with most theorems, like the intermediate value theorem, you've got to state, hey, this function is continuous. Like the mean value theorem, you've got to say this function is continuous and differentiable on the interval. So for this, you've got to show the behavior of the numerator, behavior of denominator to meet L'Hopital's condition. And once you have met it, then you can use it. Colin.
So you can do either L'Hopital or the
Why did he have to have a name like that, right?
Huh?
Why did he have to have a strange
You
name?
do that or the denominator.
Yeah, or the degree trick, yeah. So I think L'Hopital's rule is a little more versatile, I feel, because you can differentiate a lot of stuff. You know, if there was like an e to the x involved here or some cosine, all of a sudden dividing by degree of denominator doesn't really help all that much. So L'Hopital's rule is a little more adaptable, a little more versatile. But in this case, you could go either way, definitely. But like so I said, 2 folks asked about L'Hopital's rule, so I thought I'd say something about it. We'll get to it later, though. Any other questions? All right. Well, let's see if you guys can fill in the blanks. Let's see if you can make sense of this. Take a look at 3.7, optimization, and see if you can figure out what should go where. We'll start in with some examples. Oops. How about that? Optimization, finding an optimum value or finding a blank or blank. Blank and blank occur at blank points or endpoints. Blank points are places where the derivative is blank or does not exist. A lot of blanks to figure out there. I'm trying to get you to understand what we're going to be looking for, what we're going to be looking at. And then I think I've got like 4 or 5 examples for us to try. Optimization is finding an optimum value or finding a blank or blank. Max or min, yep. So we're looking for maximums or minimums here. Optimization is just a broad way of saying both. Blank and blank, what do you think goes in those 2 blanks? Maxes and mins, yep. Those occur at blank points, critical points, which we've talked about previously in this unit, or endpoints, potentially. And blank points, critical points or critical numbers, sometimes we call them, are places where the derivative is blank or does not exist. 0. Okay, so one of the challenges with these sorts of questions, and AB veterans can hopefully identify with this, one of the challenges is you've got to be really careful identifying what you are given. This is a calculus class, and so it's safe to assume that you will be calculating derivatives at some point or another. Makes sense, I hope. Yet sometimes you'll be given some scenario, some setup, and you'll actually be given the derivatives, right? They'll tell you, hey, there's such and such a rate, such and such a derivative, whatever it is. And so it's really tempting to differentiate those when you shouldn't, right? You need to identify that those are rates. So don't just like automatically start differentiating stuff because it's a calculus course. Pay really close attention. We'll talk about how you can pay close attention to what you're actually given. And then once you've identified the appropriate rates, whether you had to like actually find them or they were given to you, then all you have to do is use them to find critical points. And then we're going to analyze what's going on at those critical points, what's going on at those endpoints, and then we'll kind of move on from there and make a judgment. So a few steps here for optimization. These are just general loose guidelines here. Not all of these are going to apply. For instance, drawing a picture, sometimes that will apply. Sometimes it makes a lot of sense, other times it makes no sense. We're pretty much always going to have some kind of a primary equation that we're trying to find the min or max of. Sometimes it's given to you. Sometimes we're going to have to figure that out for ourselves. Sometimes you're going to have to use substitution to reduce the number of variables down a little bit. Realistic domain, when we're talking about real world stuff, you can't have like a negative number of cats in the vet clinic or something like that. So, 0 would be kind of the lower bound for that. So look for a boundary for the domain. And then we're going to use calculus. I know that sounds like, if you're in Sunday school and somebody asks a question, you say the answer is Jesus. We're in calculus. We're going to use calculus. I realize that's a very loaded thing, use calculus. So what are some of the methods, like if you are going to use calculus, what are some of the strategies and methods we would be using to find maxes or mins? I can think of 3. What would be the strategies for finding maxes and mins involved with the whole use calculus thing? First derivative test. Yep, that would be one of them potentially. What else? Second derivative test. Liz, also correct. That would be another one. There's one more. Kinda, sort of. I'm not sure what graph you're talking about.
Function graph.
The what graph?
If it was f of x, just looking at f of x.
Okay, yeah, I agree. I think in a lot of those situations you won't be given that. There's one. So let me ask you this. So far we've come up with first derivative test, second derivative test. What kind of mins and maxes do those techniques allow you to find? No. The critical points are like essentially analyzed by those. And I think I kind of hear what you're saying, Jeff, but like I'm looking for a very specific term, relative, right? Or what's the other word for relative? Local. Yeah, local. So relative, remember relative and local are kind of the same thing, right? Just different words to describe the same thing. And then the other kind was, I think I heard somebody say it. Was it you? What? Global. There we go. And what's the other word for global?
Absolute.
Absolute. So this might be worth talking about maybe. The difference between local and global, or the difference between relative and absolute. I had this discussion last year. Maybe it's worth talking about right now. If I were to, if we were to like stand here and look out our window, and I were to say, what's the highest elevation point you can see? I'm thinking one of those hills out there heading towards backcountry, right? I'm thinking that maybe that one over there right by the cross on Cherry Hills. That must be the highest point in the world.
True. That's a true fact.
Well, doesn't it sort of depend on how you define your world? If I define my world as anything I can see out the window, well then sure, it's absolutely the highest, right? It would be an absolute max if that's how I define my world. But if I define my world as literally the world, like the whole globe, that is just a relatively high point, right? As clearly, I think we can, I don't know if anybody's ever been there, but it's not as high as Mount Everest, right? I'm thinking not, right? I don't think anybody's ever died from high altitude sickness climbing up to the top of that hill, right? As far as we know, right? Maybe if you ran really fast, you might struggle. I don't know. But the point is this. Local and relative simply are a high point or a low point, just where you basically go from up to down. But just because you went from up to down or down to up doesn't mean that is the highest in the world or the lowest in the world. To judge is it the highest in the world or the lowest in the world, you kind of need a graph like Johnny was talking about. You need to be able to basically test the endpoints and any relatively high or low points and just see, well, which one has the highest output, which one has the lowest output, and then those are going to be our answers. So that is often referred to as the candidates test. We often make a table. Maybe that sounds a little bit more familiar. We make a table for the inputs, which would be our candidates. That's why it's called the candidates test. And we get some outputs, and we're like, hey, look, that's the highest one. And oh, right there, that's the lowest one. So these would be your 3 methods. When it says use calculus, first or second derivative test, or you could make a table. The table really only comes into play if you're going to be considering endpoints. You're going to be considering absolute extrema. Yes? Good? Okay, well, let's do some examples here. I am going to jump around just a little bit through the notes. I'm going to save number 1 for a little bit. Let's do number 2. Sometimes, well, hold on. Yeah, debating. Let's do number 3. I like number 3. Sorry. I don't mean to change my mind, but there you go. Let's do number 3. Okay, so number 3 says a farmer plans to fence a rectangular pasture adjacent to a river. Every calculus book written in the last century probably has a question like this. It's classic. Probably means there's some value to it. Pasture must contain 245,000 square meters, so the herd will have enough grass. What dimensions will require the least amount of fencing if no fencing is needed along the river? Okay. So I don't know about you, but sometimes it is pretty darn easy to get to a paragraph like this and wish that it wasn't a paragraph, and kind of be like, oh my gosh, it's like several sentences. I thought this was a math class, that kind of thing. My advice to you, similar to the advice I'd give you if we were doing a related rates question, I want to first identify what it is I'm supposed to be finding and try to make some sense out of that. What are we trying to find? Like, what is the question you're asking us to get to? Yeah. What dimensions will require the least amount of fencing? So in the end, basically, I'm going to need a length and a width for these dimensions of this rectangular field. Okay? Might be worthwhile to circle some other useful information. What else do you see that might be useful that we could then start to do some work with? Say again, area? Okay, so area equals what?
245.
Yep. As mentioned in the steps before, do you guys think this is worthy of a picture?
Yes.
I agree. I think it is. So I'm going to sketch out a picture.
Deep river. So, but like, is he just putting grass in that thing, or are there going to be animals in the tree?
There's cows. There's cows in there.
But then I feel like you would need a fourth fence. Because otherwise they could just walk across the river.
Cows are smart. They don't want to drown. It's a very scary, very fast-moving river.
How do we know that?
This is a satellite image. It's hard to tell. It's hard to tell. Okay. So Liz's picture is a degree or two better than mine, but that doesn't make me feel sad. So here we go. Guys, listen up, please. What would you guys think would be appropriate labels for something like this? X's and Y's make a lot of sense. Let's just be consistent here. Did you guys label this with an X and this with a Y? Don't you think it makes sense to have the X be horizontal, the Y be vertical? Because that's what we're used to.
Oh, I guess it
You drew your river like on the side instead of the top, but it's okay. It's okay. So here is really the most important question for giving us direction. Listen up, please. What is it exactly that we are trying to minimize? It says we need the least amount of fencing. And hopefully that makes sense because the farmer doesn't want to spend more than he needs to. But what are we really trying to minimize? Length, and it's almost a perimeter-ish idea. I mean, I realize the river supplies one side, but it is sort of a perimeter of fencing at least, right? So let's write down, this is going to be the thing we're going to optimize. This is one of those steps. Write down the equation that you're going to be optimizing, or the quantity you're going to be optimizing. So how would you guys describe the perimeter of our fencing? 2y plus x is correct. Because you got 2 y's, you got 1 x, you add them up, you get perimeter. So we're really trying to minimize perimeter. Here is where we run into some issues, and they involve the number of variables. Here's why we have a problem. If I were to try to differentiate this right now, because let's think about why I would do that. If I'm trying to minimize perimeter, wouldn't I want to find p prime and find critical numbers? So where's p prime? 0 or doesn't exist, and that whole routine. The problem is, if I'm going to find p prime, well, am I going to be doing dp dx, or am I going to be doing dp dy? Because I would have to pick. And if I was going to have to do something like this, we'd actually have to do like a calculus 3 sort of thing, where you've got multiple variables and do partial derivatives and blah, blah, blah. And because we got more information, it would actually be a lot easier just to use that other information. Okay? So if I'm going to use that other information, which is, of course, area, I can say that the area of the pasture is 245,000. What would that equal as far as our dimensions go? XY. That's right. So what I can then do is use 245,000 equals XY to substitute into the other equation. Would you guys suggest, just from making this as easy as possible for you, would you guys suggest solving for X in the area or solving for Y? You want to solve for Y? That's fine. I was just asking for your suggestion. That sounds good to me. So we're solving for Y. Is it okay with you if I write it like this? Y equals 245,000 X to the negative 1 instead of over X. All right. So now I substitute in. So perimeter equals 2 times 245,000 X to the negative 1 plus X. Still making sense? Basically, I've plugged in what Y equals for Y. Dylan, is that okay?
Yeah, that's fine.
Okay. So then we do a little bit of cleanup work here. Perimeter then equals 490,000 X to the negative 1 plus X. And now, finding the P prime is actually quite clear now because P is in terms of just one variable instead of two. So P prime equals negative 490,000 X to the negative 2 plus 1. And why on earth would I, other than the fact that it's a calculus class, why would I be interested in the rate of change of perimeter? What am I going to do with it? Find the minimum of what? Perimeter. How is P prime going to help me find the minimum of perimeter? Can find the critical points. And how do I find the critical points? Yeah, set it equal to 0, but let's also consider, are there any x values for which P prime doesn't exist? 0, when x is 0. Isn't this a denominator right here? So when x is 0, P prime doesn't exist, but I think we can safely ignore that. Why could we ignore that in this case? Yeah, there would be no place for the cows, right? If x is 0, there's no area, right? That would actually be a minimum, wouldn't it? We're trying to have the least amount of fencing, not the least amount of area, right? Okay, so I'm going to set this equal to 0. And believe it or not, when we've done questions like this in the past, everybody seems okay with, hey, we found P prime, we set it equal to 0 and all that. The algebra that follows is always like I'm sort of uncomfortable, right? So what would you guys do with P prime equals 0? What would you do as far as getting ready to solve for x? Say again? You can do this without a calculator. Say again?
Subtract negative 1 over.
All right. So negative 490,000 x to the negative 2 equals negative 1. All right. He's kicking the can down the road. What next? That negative 490,000? Okay. So that would give me x to the negative 2 equals positive 1 over 490,000 because a negative over a negative ends up being a positive. We have successfully kicked this can all the way down the road. We finally have to deal with the negative exponent, right?
Take a reciprocal of everything. Reverse it.
Like flip both sides?
Yeah.
Johnny's doing this with his fingers.
Yeah.
Flip both sides. He's right. So if I flip the left side, I get x squared. And if I flip the right side, I get 490,000. You can only do this when you have a single term on the left and a single term on the right, which we do, so it works. And then finally, the easy step here is just square root both sides. So x is equal to 700. Bless you, Liz. So that's a critical point, right? It's the only critical point. Let's make note of a realistic domain here. Having the fencing, like having the x dimension be 0, as we already mentioned, makes no sense, right? So we can't go down to 0. So we're bounded really by positive x values. How high could the x values go? Well, no, the x values could go way over 245,000 if the y's were less than 1, right? So if the y was only like half of a meter, then the x could be 490,000. Where are we headed with that? There's really no bound to that, right? And so it's like sort of unrealistic to think of an upper bound. And so I say all that to say we're really only looking for what amounts to a relative extrema. But since it's the only critical number in town, so to speak, then it's also going to be the absolute least amount of fencing as well. So anyways, we just have to prove simply that x equals 700 provides perimeter with a minimum. Would you guys prefer to use a first derivative test or a second derivative test? Really? Isn't a second derivative test easier? This is opinion, so we could disagree, and that's okay. I think the second derivative test would be easier simply because it's really easy to find the second derivative. So take that for food for thought there, but you can use the first derivative test if you want. I would just say that p double prime is equal to positive 980,000 x to the negative 3 plus 0 technically. So all I really have to do here, I could use my calculator to find p double prime of 700, which would equal 980,000 over 700 to the third. Would you have that?
No.
You got to use a calculator for this, obviously.
Yeah.
What do you get, Alexander?
Wait, why is
Not at all.
So according to Cole,
You get it. Be weird.
you guys agree with Cole? I heard the same number over there coming from somebody. Okay. Thank you. Hey, what's the most important thing about that number? It's positive. So since p double prime is positive, it means what is concave up? Be super careful. Think about how ambiguous this is. P double, listen please, hey, listen. Think about how ambiguous this is. P double prime is positive, therefore concave up.
Of course.
Like if we follow exactly what you just said, you're telling me that P double prime is positive, therefore concave up. You're telling me that P double prime is concave up, which may or may not be true, but it is not important at all. We don't really care if P double prime is concave up. We would want to know if P is concave up. So be really careful about, therefore, some unnamed thing is concave up, and you don't even have to say that. So all you really have to say is because P double prime is positive, you could say, therefore, P is concave up at x equals 700. Therefore, P has a relative minimum. This is the second derivative test. At x equals 700. It did ask for the dimensions of the field, like both dimensions. We have the x equals 700. How could you find the y equals whatever?
to the area equation?
Plug it back into the area, like the thing we used to substitute with. Bless you. Yeah. So if you take that 700 and you plug it back in, maybe right there, you'd get your y value out. 245,000 over 700. Sounds like it'll come out nice. What is it? 350. Okay, yeah. So your dimensions would be 700 meters. Yeah, meters by 350 meters. That will provide the area that we want, but at a minimum amount of fencing. It's really a handy thing to know as far as trying to minimize your cost for the fencing. Okay, so pretty involved one right there with the substitution, some fairly detailed work with the actual rule for the functions, so on and so forth. Hey, let's go back to number 2. Let's go back and do number 2. This is the flow rate of traffic question. Why don't you guys try this one on your own, number 2. There it is. Okay, we're trying example number 2. Please try this on your own or with a friend. Pretty far through this. You know, here's the thing that people will kind of trip up on this one is, you know, it says on a given day the flow rate F in cars per hour. And they'll look at this and they'll be like, hey, I just identified that we have a rate, a flow rate, And that's a rate. And so maybe this is one of those questions in which the derivative has already been given to me. But I want you to look really carefully and identify what we're trying to do. It says, what speed will maximize the flow rate? So we are trying to maximize flow rate. And here's kind of the trick. We're actually trying to maximize a rate, right? We're trying to maximize a rate. And so even though we were given a rate, we're still going to have to find a derivative. We're still actually going to have to calculate the derivative ourselves. So this one can be a little bit tricky from that perspective. So if we're trying to maximize flow rate, let's again kind of think of a realistic domain here. What would be kind of like a lower bound for the speed, like the v here? What would be a lower boundary? 0, yeah. Speed can't be negative. And so, yeah, the lower bound for v has got to be 0. So it's got to be non-negative, right? Positive or 0. What's the upper bound? How high could the speed be? Right, there's really no bound for it, right? We're hoping that, I'm really hoping that the speed that would maximize flow rate isn't like 12,000 miles an hour because, you know, for obvious reasons. So we'll just have to see how this goes. Yeah, if you had airplanes, like hypersonic airplanes or whatever. No longer a road. Hey guys, let's finish this up. Hey, let's finish this up well. So if I'm going to try to maximize flow rate, and I know that flow rate is equal to V over 22 plus 0.02 V squared. If I'm trying to maximize flow rate, I need to know flow rate prime. And so if I am going to find this F prime, what rule could or should I use? Quotient makes sense. You could flip up and do a chain product combo, but I think quotient makes a lot of sense here. So it's going to be low, D high. D high would just be 1 minus high, D low. D low would be 0.04 V over the square of what's below. So guys, we've already decided that there... Oh, sorry. We've already decided that there's no, like really, practically speaking, lower bound or upper bound. And so we're really only going to be searching out critical numbers. So are there any values of V for which F prime doesn't exist? No, there aren't, because 22 is positive plus something, and V squared has to be positive. So the denominator is just going to be positive regardless of what you plug in for V. So it could never be 0. So I'm going to just set this equal to 0, but I'm going to clean things up here a little bit before I actually work on solving. F prime equals, it's going to be 22 minus 0.02 V squared. This would be where you could be duped into making a really bad cancellation. They're different though, right? And this equals 0. Here's where you could really twist yourself up, but ask yourself the question, what part of a fraction is the only part that could make the whole fraction have a value of 0? Only the numerator, only the top. And so what I'm going to do is take this and set the numerator equal to 0 and solve. So 22 equals 0.02 V squared. Divide both sides by 0.02. Square root both sides. 33.166. Okay, so 33.166 equals V. That sounds reasonable. Thankfully, it's not 12,000. What have I found at this point? I found a critical point. I have not proven at all that this particular value for speed will maximize flow rate. What could I use to help me decide that it actually does? Say again? You could do a second derivative test. You could do a first derivative test. Which do you think could be easier here? I think first is, because I think finding a second derivative is going to involve another quotient rule, which is not that big of a deal, but it'll also involve a chain rule in there too. Or you could FOIL the whole denominator out. Neither of which is that pleasant. Calculator's active. We need to create an interval with 33.166 inside there. what would you guys suggest is a lower interval number? Like what should we plug in to set up our first derivative test? 0, okay. I don't know, how does 0 work out? Well, you get, what, 22 over 22 squared? What is that? 0.04? 0.045. Okay. What would be the most important thing about that number? It's positive. And then we want to also establish a number, that's a number to the left of our critical point. What is the number to the right? That might be too close. I mean, it might, I don't know. If that number ends up being negative, then we have a clear indicator. I make it simple on yourself. How about 34? 35? 40? What are you guys going to do? Josiah, your question while they figure stuff out.
I was just saying, I don't think that I got a different answer for the velocity.
For the 33.166?
Yeah, because I graphed it, but I think what you did is you made the top a 0.02 and it was a 0.04.
I actually agree with this.
Yeah,
I think that it's 24.061.
No, I disagree. So if you take this and this, so this right here is minus 0.04 v squared.
Yeah.
And then when you add these two,
sorry.
you end up, so you have positive 0.02 minus 0.04. I think you get minus 0.02.
Oh, yes. I was going to say, if you graph it, why would you get a different answer? Is that
You shouldn't.
because of the denominator?
You should
I don't think I did.
double check it. That 33.166 sticks out of my mind as being right. Double check your graph. We'll come back to you. Hey guys, what'd you plug in for an upper interval? 40. Okay, so what's f prime of 40? Negative 1 point, you said?
Negative
0034. Okay. So the most important thing about that number is that it is negative. So we could go down here and say something like this for a conclusion. Because f prime of 33.166 equals 0, and f prime changes from positive to negative. At that critical point, because that's true, f is maximized at v equals 33.166. Something along those lines. So that's probably best practice. Like if it were a quiz or test, I'm going to be really explicit. I'm going to say, please include units with your answer or something like that. So I didn't really say that here. It is best practice, though, to put units with it. So if you wanted to put, miles per hour, right? Because we're looking for that for the units for V at least. MPH. Makes sense? Yeah. All right. Is this making sense? Colin, question. Yes, you certainly could. Just make sure you're writing. If the calculator is active, obviously that's an option. Just make sure you're writing down, hey, I found that f double prime of 33.166 is, and just word your justification, and that's fine. All right. Any other questions? Okay. Let me decide what I want to do here. Let's do, so when I see you guys tomorrow, we'll finish up number 4. I just want to do the first part of number 4 here, kind of get some momentum going in the right direction. So flip over to number 4, please. And we'll catch back up with number 1. I think number 1 is one of the more challenging ones for sure. So this says, this is a classic example, right? This is another one, like you see these all the time. The tide removes sand from Sandy Point Beach at a rate modeled by R, given by R of t. So the water is dragging the sand out to the sea, but a pumping station is adding sand to the beach at a rate modeled by S. You might think this is unrealistic, yet it's totally realistic. When a hurricane washes a beach away, do you know what they do? They rebuild the beach by pumping sand back to where the beach used to be. Do you think that might be important for a tourist destination? I went to school in Florida. Hurricane hit, beach gone. They just pump sand back on and rebuilt the beach. This is like totally realistic. You might look at it and say, what, pumping sand onto a beach? Yep, they definitely do it. So you got S of t right there. Both R and S are cubic yards per hour. T is on the interval from 0 to 6. At time t equals 0, the beach contains 2,500 cubic yards of sand. So I think that the first bullet point is a pretty nice one to finish on. It says, find the rate at which the total amount of sand on the beach is changing when t equals 4. So it says, that keyword find the rate at which the amount of sand is changing. There's two different rates though, right? So how do we combine the two different rates? S of t. So Jasmine, you answered that pretty quick. Why did you make it S minus R instead of R minus S?
S is coming in and R is going out.
Yeah, isn't S making there be more sand on the beach? But R is making there be less sand? And so we're always going to situate it like you said there, that's well organized. I want to know what's going on at 4. So I'm going to use my calculator to find S of 4 minus R of 4. I wanted to do this one. I hope that you'll just leave these equations in your calculator because tomorrow we'll use these equations again. So S of 4 minus R of 4. Anybody have a value for that?
Negative 1.909.
9 what 9?
909.
909? You got to be in rating mode. Hopefully you are. Does that number, I heard like 3 people say it. Is that good?
Yeah.
Okay, so what is the most important thing about that number? Therefore, we can say that the amount of sand on the beach, it didn't ask this, but the amount of sand is doing what? Decreasing, yep. It didn't ask you to go there, but I thought maybe I'd connect that for you. Now it's decreasing because its rate of change is negative. So guys, when you come back tomorrow, we'll continue to use these equations, and we will talk about minimums and maximums, and we'll start talking about endpoints. We'll also talk about Newton's method. Make sure you watch the video. Have a good day.